Hi, I'm Dr. Chris Creighton, and in this video we're going to talk about polynomial functions in functional algebra. The core objectives are performing polynomial algebra, which is adding, subtracting, multiplying, dividing. Same thing with functions in general, not just with polynomials. And then in the second part, we'll talk about the composition of two functions. That's when you plug in one function into another function. So first, what is a polynomial? So a polynomial is of the form a(n) x to the n plus a(n) minus 1 x to the n minus 1 plus dot dot dot, which means the pattern continues, a1 x plus a0. And typically this is written as y is equal to that. Some features. This is called the leading coefficient. This n is called the degree. This last term here is called the constant term because it doesn't have a variable on it. And usually we'll write this in descending order. So polynomials are things that look like x to the 8 squared, x cubed, and so on. So for example, y is equal to 3 is a polynomial. Y is equal to 2x minus 1 is a polynomial. Y is equal to, let's see here, x to the 4th minus x cubed plus 2 is a polynomial. And for each of these, the degree here is 0, because it's, if you want to think about it, it's x to the 0 is the leading term, is the degree. The degree here is 1 because this is linear, that's the line. And the degree here is 4. It's an x to the 4th power. So polynomials look rather nice like this. Things that are not polynomials, y is equal to the square root of x minus 1. This cannot be written as x to the n or a sum of things that look like x to the n. So this is not a polynomial. Another one, y is equal to 1 over 2 minus x is not a polynomial. This one also cannot be expressed as a sum of terms adding up of x to the n. So those two things are the key two that are not polynomials. There are other things that we'll talk about later, such as exponential functions. And logarithms, those are also not polynomials. Polynomials are things that are of the form x to the n, where the n is some integer being, or natural number being 1, 2, 3, 4, 5, and so on, starting at 0. So what's really nice about polynomials, and we've already dealt with this a little bit, is evaluating and graphing them. They're quite nice to graph in that you can just start picking points and then plotting said points. So for example here, I want to graph the polynomial negative x squared plus 1. This is a degree 2 polynomial, which has some nice features. It's also known as a quadratic polynomial, being that it has degree 2 for the quad there. And then what's nice about these two is that when you start plugging in things, it gives you really nice values. So for instance, I'm going to start off with picking some values. So let's do negative 2, negative 1, minus 1/2, because you can plug in anything to these. 0, 1/2, 1, and a 2. Extend that line down a bit. So the key feature is the domain of polynomials is all real numbers. Negative infinity to infinity, or all real numbers. So that's a key feature to keep in mind here when you're dealing with these. You can plug in legitimately any real number to these and get a value. So doing these ones, so plugging in minus 2, so this is minus negative 2 squared plus 1. Well, that's equal to 4, so that's minus 4 plus 1, which is equal to minus 3. Likewise, we have minus 1, plugging in minus 1 plus 1, which is equal to minus 1 plus 1, which is equal to 0. Plugging in that 1/2 here, plus 1. Well, that is minus 1/4 plus 1, which is equal to 3/4. 0 is quite nice, so plugging in 0, I get just the value 0 plus 1, which is equal to 0. And then for these ones, you should see some mirroring happening here, and that's because of some features of this quadratic. So we get a negative 1/4 plus 1, which is equal to 3/4 again. Plugging in the 1, we also get minus 1 plus 1, which still gives us 0. And then plugging in the 2 squared, we'll get minus 4 plus 1, which is equal to minus 3. So you'll start to see some symmetry for these. Not all polynomials have such nice symmetry, so it's not going to look so nice around 0. It's not going to behave the same on either side. It really depends upon the polynomial. This one has some symmetry around 0, which you can notice. I just turned the grid on so we can graph these. So now we are starting to plot the points. So we have the point negative 2, 3. So we come down here to negative 2. So negative 1, negative 2, negative 3. So we have this point there. That is the point negative 2, negative 3. Then at negative 1, we're here at 0. That's pretty nice. At negative 1/2, we're at 3/4, so it's like right up in there. At 0, we're at 1. At 1/2, we're again at 3/4. At 1, we're at 0. At 2, we're at negative 3. So this should be enough information to get what the picture looks like. So playing connect these, we know it at least looks like that. And what's nice about polynomials is that if you've captured all the key features, you can just assume that this comes down as well. And that's the rough idea on how to graph polynomials. There are other techniques for polynomials, but for us right now, if you're asked to graph a polynomial, you'll make a table of values and make sure you pick enough values to get all the features. So for instance, don't just pick 1, 2, and 3, or negative 1, 0, and 1. Pick enough to get all the right features, get the scaling on it as well. So now that we know and have reminded ourselves on how to graph and evaluate polynomials, let's get into some functional algebra. So functional algebra is the idea that we can add, subtract, and multiply and divide functions, just like we can do with like polynomials. So for instance, here I have two polynomials. The first one is f of x, which if you are not familiar with functional notation, please go back and review that. But here we have f of x is equal to 2x plus 1, and g of x is equal to x squared plus x. So say we want to do an operation. So something like f plus g at 2. And so what that is asking us is that we're going to add the two functions named f and g together to get a new function named f plus g and then evaluate it at 2. But functional algebra, when you do it, this is actually it's f of 2 plus g of 2. So the first thing we need to do here is to evaluate both f and g at the value 2. Doing that quickly, f of 2 is equal to 2 times 2 plus 1, well, that's equal to 5. That's pretty nice. In g of 2, we get 2 squared plus 2, which is equal to 6. Also fairly nice. So in this case here, what this is equal to is the value of f at 2, which we found was to be 5, and then the value of g at 2, which we found to be 6. So the sum of these two functions is 11. So to repeat, the way to evaluate two functions added together is to evaluate the two functions at the given point and then add the values. So this is operating on the outputs of the functions and not the inputs. So similarly, if we want to do f minus g at 2, this is subtracting the function. So this is f of 2 minus g of 2. So this is sort of the definition. To subtract the two functions, you subtract the values of the two functions. So in this case here, we get 5 minus 6, and that's equal to minus 1. So if instead of adding the two functions together, where we add the outputs of the function at 2, we subtract them from each other. Likewise, f times g at 2. And I just wanted to note here, typically with functional algebra, there is not a symbol between them, but sometimes there may be a dot, like such, to indicate that it's multiplied. This is thinking about later on in the next video, where we'll be talking about functional composition, which there is a symbol there. So with f times g, so this is multiplication, this is f of 2 times the value of g of 2. And sometimes I want to think about this as those things are multiplied together. So in this case here, we have 5 times 6, which is equal to 30. And then lastly, we have f divided by g of 2. And I want to note, this must be provided that g of 2 is not 0, because you can't divide by 0, which is fortunate in this case here, where g of 2 is 6, but it can happen that you're dividing by 0. So in this case here, this is f of 2 divided by g of 2, which is equal to 5 divided by 6, which is rather nice. So that was doing it with plugging in values. But another thing that we can do here is say f plus g of x. And so what this is saying is that we're taking the two values in general for any value of x and then adding them together. So we're saying for whatever choice of x is, we're going to be adding the outputs of values. And what's nice about this, given that our two functions are given by polynomials, is that when we add these together, we'll get another polynomial. So in this case here, this is equal to, and I always like to put this in parentheses, 2x plus 1 plus an x squared plus x. So we're adding the two values together, f plus g of x. So the first one here is our f of x, and the second one here is our g of x. And we're adding them together. And now this turns into polynomial algebra, which is quite nice. So this is equal to x squared plus 3x plus 1. So when we added the two functions together, this holds in general, we add the two values, so like the two equations together. And then one interesting feature of this is that we can do f plus g of 2 and plug it into this function here. And we should get the same thing, x squared plus 3 times 2 plus 1. Well, that's 4 plus 6 plus 1, which is equal to 11. So perfect, that worked out great. So this new equation actually holds for any value of x. So we don't have to keep going back and be like, okay, what's f of 3 and g of 3, then adding those values together. The benefit of this is now we have an equation defining the sum of the two original functions. Likewise, if we were to do multiplication, f times g of x, so this is going to be equal to 2x plus 1 times an x squared plus an x, which in this case is our f of x times our g of x. So multiplying this out, this is equal to 2x cubed plus an x squared plus a 2x squared plus an x, which simplifies down nicely as 2x cubed plus 3x squared plus an x. So again, this notation means that we're multiplying the two polynomials together, and that turns into a polynomial multiplication. So we can also check this at 2, because we already know what the value of this is. It should be 30. So this is equal to 2 times 2 cubed plus 3 times 2 squared plus 2. So 2 cubed is 8 times 2, that's 16. 2 cubed times 3 is 12. Plus another 2, and that is in fact 30. So this gives us a nice formula for the multiplication as well.